Welcome to clickmyproject.com. Let's discuss about the product. Our product is bio-inspired glucose control in diabetes based on an analog implementation of beta cell models. This paper presents a bio-inspired method for in vivo control for blood glucose based on model of the penetric beta cell. The proposed model is to be implementable using low power analog integrated circuits in CMOS, realizing in biologically faithful implementation and which captures all the behavior seen in physiology. This is the implementation to be capable of glucose control using an in silico population of diabetic subjects, achieving up to 93% of the time in tight glycemic target. That is, glycemic target is represented between 70 to 140. The proposed controller is the compared with commonly used external physiological insulin delivery controller. For glucose control purposes, these comparisons performed. Results confirm equivalent or superior performances in comparison with our previous physiology insulin delivery, that is EPID. The system has been designed in a commercially available 0.35 micrometer CMOS process and achieves an overall process consumption in power ranges of 1.907 milliwatt. The circuit is an electronic realization of the original beta cell model equations, which is achieved with the use of several blocks. That blocks are low-pass filter, multiplier, transconductance, thermocoder, and comparator. Each block consists of the different current value, which will give the different power value of each block. Based on the total beta cell power consumption, can be reduced the implementation of bio-inspired glucose control in diabetes. Diabetes mellitus is one of the most rapidly growing chronic disease in modern society, affecting 3 to 5% of the total population on earth. It is normally characterized by an increase in blood glucose, which occurs either because the pancreas does not produce enough insulin or because the producer's insulin is not functional. Type 1 diabetes mellitus, that is T1DM, which amounts to 10% of the diabetic population, is an autoimmune condition which results in complete destruction of insulin secreting beta cells. If the left unmanaged, it can have long-term side effects such as blindness, kidney failure, and heart diseases. Current treatment of T1DM involves insulin injection after meals using an insulin pen or an insulin pump. Although this works in the short term, subjects will still spend a large amount of time with high blood glucose or hyperological, putting them at risk. A continuous blood glucose sensor, which is connected to the body either subcutaneously or intravascularly. An insulin pump that delivers insulin either subcutaneously and intravenously. A device which runs a control algorithm to relate the rate of delivering insulin with blood glucose level. The biostator was one of the first artificial system which introduced before 40 years. Due to its intravenous nature, it was only used in clinical by the patient's bedside and was very useful in a wide range of medical studies such as assessment of the influence of drugs on health, on measurement insulin resistance using clamp techniques, and treatment assessment on surgical investments. And since the initial creation of the biostator, there has been an evaluation in portable subcutaneous continuous glucose monitoring and insulin pump technologies, allowing subjects with diabetes to manage their blood glucose outside the hospital environment in the open loop fashion. There are still suboptimal, however, with subjects still spending a large amount of time with high blood glucose levels. As a result, there have been several attempts to create an artificial pancreas, all working with existing subcutaneous glucose sensors and insulin pumps. These, however, have to accomplish an inaccuracies of glucose measurements, making their adaptation challenging. More recently, we have seen the advent of which would potentially allow faster control of blood glucose with minimal delay. Let's see the black diagram of our system. So this is the flow of our proposed design methodology. As we already discussed, our design methodology is based on CMOS designing. For the CMOS designing methodology, we have to use Tanner EDA as an implementation tool. So as we previously seen, there are a lot of blacks in this overall design, such as low pass filter, multipliers and comparators. They are named here as block H, block F, such a things. So these are the submodules blacks. So overall submodules and overall blocks give us a bio-inspired glucose control system. So after we designing each block by block, finally we have to design low pass filter, multiplier, that means block H, block F and comparator. So each blocks are designed separately and they simulated separately. Each block gives different voltage performance and different results. So all the blocks gives us different results, and each block simulated and each results from the each blocks are verified and compared with the previous system designs. Let's discuss something about the tool. For this CMOS design based methodologies, we have to use CMOS design tool, that is called Tanner EDA tools. Commonly, Tanner EDA tools having lot of subdivisions, that is called SEdit, LEdit, WEdit and such more. There are lot of under devices. So in this we are using SEdit for circuit designing. So and then after we design that SEdit, while simulating, the circuit's design will pass through the T-space that we can understand through the checklist generated through the SPICE code. And finally, while we are simulating, the timing diagrams will appear in WEdit. Hence, commonly for our CMOS based designs, we will use mostly these three edit things. That is, again I will say as SEdit, LEdit, WEdit and T-space. So we can design the circuit based CMOS transistors by using SEdit. Here, before we starting the simulation, we have to select a new cell. Here is the cell menu. Here we have to select the cell menu and we have to select new cell. So there you can select number of cells like cell 0, cell 1 up to cell n you can select. So each cell should contain different CMOS design. And next process is to set up simulation. Here this icon, while you are pressing that will leads you to setup simulation. In the setup simulation, you have to set up maximum time duration for the design and nanoseconds based setup methodologies. After designing setup designs, we have to load the library files. So initially for the design of CMOS designs, we need some CMOS components. Those CMOS components will occupy in CMOS libraries. That means CMOS libraries contains components of which required for CMOS design. So here you can see what are the components listed in CMOS library. While you are pressing add, it will leads you a window menu. There you can locate the library file where you have stored. So from the location where you have stored, you can select all components which you can need for your CMOS design. So after design of this cell, you can save the design, and while you are pressing run, it will leads to T-space. So through T-space, you can see what are the checklists available in T-space. In T-space, usually the components which you have used are listed in as a component code. That means you can see that as a program wise. That's why that T-space codes are called netlist. You can run either from SEdit or from T-edit. From wherever you are running, the output timing diagrams will show in WEdit. In WEdit you can see the waveforms which we have obtained for corresponding CMOS design. And also you can clarify what are the result parameters, and you can measure all the parameters which you need for the design from the WEdit. Thank you.